At the dawn of the 19th century, in a cellar in Mayfair, the most famous scientist of the time, Humphrey Davy, built an extraordinary piece of electrical equipment. 4 meters wide, twice as long, and containing stinking stacks of acid and metal. It had been created to pump out more electricity than had ever been possible before. It was, in fact, the biggest battery the world had ever seen. And with it, Davy was about to propel us into a new age. That moment would take place at a lecture at the Royal Institution in front of hundreds of London's great and good. Filled with anticipation, they packed the seats, hoping to witness a new and exciting electrical wonder. But what they would see that night would be something truly unique, something they'd remember for the rest of their lives. Using just 2 simple carbon rods, Humphrey Davy was about to unleash the true potential of electricity. Electricity is one of nature's most awesome phenomena, and the most powerful manifestation of it we ever see is lightning. This is the story of how we first dreamed of controlling this primal force of nature, and how we would ultimately become its master. It's a 300-year tale of dazzling leaps of imagination and extraordinary experiments. Tens of thousands of volts passed across his body and through the end of a lamp that he was holding. It's a story of maverick geniuses who used electricity to light our cities, to communicate across the seas and through the air, to create modern industry, and to give us the digital revolution. But in this film, we'll tell the story of the very first scientists who started to unlock the mysteries of electricity. There's something alive in there. They studied its curious link to life, built strange and powerful instruments to create it, and even tamed lightning itself. It was these men who truly laid the foundations of the modern world. And it all started with a spark. Imagine our world without electricity. It will be dark, cold, and quiet. In many ways, it will be like the beginning of the 18th century, where our story begins. This is the Royal Society in London. In the early 1700s, after years in the wilderness, Isaac Newton finally took control of it after the death of his arch-enemy, Robert Hooke. Newton brought in his own people to the key jobs to help shore up his new position. The new head of demonstrations there was 35-year-old Francis Hawksby. Notes from the Royal Society in 1705 reveal how hard Hawksby tried to stamp his personality on its weekly meetings, producing ever more spectacular experiments to impress his masters. In November, he came up with this, a rotating glass sphere. He was able to remove the air from inside it using a new machine, the air pump. On his machine, a handle allowed him to spin the sphere. One by one, the candles in the room were put out. And Francis placed his hand against the sphere. The audience were about to see something amazing. inside the glass sphere, a strange ethereal light began to form, dancing around his hand. A light no one had ever seen before.
Oh, that's fantastic. You see a beautiful blue glow. It's just marking out the shape of my hands, but then going right round the ball. It's as though there's something alive in there.
It's difficult to really understand why this dancing blue light meant so much. But we have to bear in mind that at the time, natural phenomena like this were seen to be the work of the Almighty.
This was still a period when, even in Isaac Newton's theory, God was constantly intervening in the conduct of the world. And so it made sense for a lot of people to interpret natural phenomena as acts of God.
So when a mere mortal meddled with God's work, it was almost beyond rational comprehension. Hawksby never realised the full significance of his experiment. He lost interest in his glowing sphere and spent the last few years of his life building ever more spectacular experiments for Isaac Newton to test his other theories. He never realised that he'd unwittingly started an electrical revolution. Before Hawksby, electricity had been merely a curiosity. The ancient Greeks rubbed amber, which they called electron, to get small shocks. And even Queen Elizabeth I marvelled at static electricity's power to lift feathers. But now, Hawksby's machine could make electricity at the turn of a handle, and you could see it. And perhaps even more importantly, his invention coincided with the birth of a new movement sweeping across Europe, called the Enlightenment. Enlightened intellectuals used reason to question the world, and their legacy was radical politics, iconoclastic art, and natural philosophy, or science. But ironically, Hawksby's new machine wasn't immediately embraced by most of these intellectuals, but instead by conjurers and street magicians. And those with an interest in electricity called themselves electricians. One story tells of a dinner party attended by an Austrian count. The electrician had placed some feathers on the table and then charged up a glass rod with a silk handkerchief. He then astonished the guests by lifting up the feathers with the rod. He then went on to charge himself up using one of Hawksby's electrical machines and gave the guests electric shocks, presumably to squeals of delight. But for his pièce de résistance, he placed a glass of cognac in the centre of the table, charged himself up again, and lit it with a spark from the tip of his finger.
There was a trick called the electrical beatification, in which the victim sits on an insulated chair, and above his head hangs a metal crown that doesn't quite touch his head. And then if the crown is electrified, then you get an electric discharge around the crown that looks exactly like a halo, which is why it's called the electric beatification.
As England and the rest of Europe went electricity crazy, the spectacles grew bigger. And the more curious electricians started to ask more profound questions. Not only how can we make our shows bigger and better, but how can we control this amazing power? And for some, can this incredible electrical fire do more than just entertain? One of the first early breakthroughs would never have happened had it not been for a terrible accident. This is Charterhouse in the centre of London. Over the past 400 years, it's been a charitable home for young orphans and elderly gentlemen. And sometime in the 1720s, it also became home to one Stephen Gray. Stephen Gray had been a successful silk dyer from Canterbury. He was used to seeing electric sparks leap from the silk, and they fascinated him. Unfortunately, a crippling accident ended his career and left him destitute. But then he was offered a new life here at Charterhouse, and with it, the time to perform his own electrical experiments. Here at Charterhouse, possibly in this very room, the Great Chamber, Stephen Gray built a wooden frame. From the top beam, he suspended 2 swings using silk rope. He also had a device like this, a Hawksby machine, for generating static electricity. Now, with a large audience in attendance, he got one of the orphan boys who lived here at Charterhouse to lie across the 2 swings. Gray placed some gold leaf in front of him. He then generated electricity and charged the boy through a connecting rod. Gold leaf, even feathers, leapt to the boy's fingers. Some of the audience claimed they could even see sparks flying out from his fingertips. Show business indeed. But to the curious and inquiring mind of Stephen Gray, this said something else as well. Electricity could move. From the machine to the boy's body, through to his hands. But the silk rope stopped it dead. It meant the mysterious electrical fluid could flow through some things, but not through others. It led Gray to divide the world into 2 different kinds of substances. He called them insulators and conductors. Insulators held electric charge within them and wouldn't let it move, like the silk, or hair, glass, and resin, whereas conductors allowed electricity to flow through them, like the buoy, or metals. It's a distinction which is still crucial even today. Just think of these electric pylons. They work on the same principle that Gray deduced nearly 300 years ago. The wires are conductors. The glass and ceramic objects between the wire and the metal of the pylon are insulators that stop the electricity leaking from the wires into the pylon and down to the earth. They're just like the silk ropes in Gray's experiment. Back in the 1730s, Gray's experiment may have astounded all who saw it, but it had a frustrating drawback. Try as he might, Gray couldn't contain the electricity he was generating for long. It leapt from the machine to the boy and was quickly gone. The next step in our story came when we learnt how to store electricity. But that would take place not in Britain, but across the Channel in mainland Europe. Across the Channel, electricians were just as busy as their British counterparts, and one centre for electrical research was here in Leiden, Holland. And it was here that a professor came up with an invention that many still regard as the most significant of the 18th century, one that, in some form or another, can still be found in almost every electrical device today. That professor was Pieter van Musschenbroek. Unlike Hawksby and Gray, Musschenbroek was born into academia. But ironically enough, his breakthrough came not because of his rigorous science, but because of a simple human mistake. He was trying to find a way to store electrical charge ready for his demonstrations. And you can almost hear his train of thought as he tries to figure this out. If electricity is a fluid that flows a bit like water, then maybe you can store it in the same way that you can store water. So Musschenbroek went to his laboratory to try to make a device to store electricity. Musschenbroek started to think literally. He took a glass jar and poured in some water. He then placed inside it a length of conducting wire, which was connected at the top to a Hawksby electric machine. Then he put the jar on an insulator to help keep the charge in the jar. He then tried to pour the electricity into the jar, produced by the machine, via the wire, down through into the water. But whatever he tried, the charge just wouldn't stay in the jar. Then one day, by accident, he forgot to put the jar on the insulator, but charged it instead while it was still in his hand. Finally, holding the jar with one hand, he touched the top with the other and received such a powerful electric shock he was almost thrown to the ground. He writes, "It's a new but terrible experiment which I advise you never to try. Nor would I, who've experienced it and survived by the grace of God, do it again for all the Kingdom of France." So I'm going to heed his advice, not touch the top, but instead see if I can get a spark off of it. The sheer power of the electricity which flew from the jar was greater than any seen before. And even more surprisingly, the jar could store that electricity for hours, even days. So in honor of the city where Musschenbroek made his discovery, they called it the Leyden jar. And its fame swept across the world.
And very rapidly from 1745 through the rest of the 1740s, the news of this, it's called the Leyden jar, goes global. It spreads from Japan in East Asia to Philadelphia in Eastern America. It became one of the first quick, globalized scientific news items.
But although the Leyden jar became a global electrical phenomenon, no one had the slightest idea how it worked.
You have a jar of electric fluid, and it turns out that you get a bigger shock from the jar if you allow the electric fluid to drain away to the earth. Why is the shock bigger if the jar's leaking? Why isn't the shock bigger if you make sure that all the electric fluid stays inside the jar? That was how mid-18th century electrical philosophers were faced with this challenge.
Electricity was without doubt a fantastical wonder. It could shock and spark. It could now be stored and moved around. Yet what electricity was, how it worked, and why it did all these things was nothing less than a complete mystery. Within 10 years, a new breakthrough was to come from an unexpected quarter. From a man politically and philosophically at war with the London establishment. And even more shockingly for the British electrical elite, that man was merely a colonial, an American. This painting of Benjamin Franklin hangs here at the Royal Society in London. Franklin was a passionate supporter of American emancipation and saw the pursuit of rational science, and particularly electricity, as a way of rolling back ignorance, false idols, and ultimately his intellectually elitist colonial masters.
And this is mixed with a profoundly egalitarian democratic idea that Franklin and his allies have, which is this is a phenomenon open to everyone. Here's something that the elite doesn't really understand, and we might be able to understand it. Here's something that the elite can't really control, but we might be able to control. And here's something above all, which is the source of superstition. And we, rational, egalitarian, potentially democratic intellectuals, we will be able to reason it out without appearing to be the slaves of magic or mystery.
So Franklin decided to use the power of reason to rationally explain what many considered a magical phenomenon, lightning. This is probably one of the most famous scientific images of the 18th century. It shows Benjamin Franklin, the heroic scientist, flying a kite in a storm, proving that lightning is electrical. But although Franklin proposed this experiment, he almost certainly never performed it.
Much more likely is that his most significant experiment was another one, which he proposed but didn't even conduct. In fact, it didn't even happen in America. It took place here in a small village north of Paris called Marly-le-Ville.
The French adored Franklin, especially his anti-British politics, and they took it upon themselves to perform his other lightning experiments without him. I've come to the very spot where that experiment took place.
In May 1752, Georges-Louis Leclerc, known across France as the Comte de Buffon, and his friend Thomas-Francois Delibar erected a 40-foot metal pole, more than twice as high as this one, held in place by 3 wooden staves just outside Delibar's house here in Marly-le-Ville. The metal pole rested at the bottom inside an empty wine bottle.
Franklin's big idea had been that the long pole would capture the lightning, pass it down the metal rod, and store it in the wine bottle at the base, which worked as a Leyden jar. Then he could confirm what lightning actually was. All his French followers had to do was wait for a storm. And then on May 23rd, the heavens opened.
At 12:20, a loud thunderclap was heard as lightning hit the top of the pole. An assistant ran to the bottle. A spark leapt across between the metal and his finger with a loud crack and a sulphurous smell, burning his hand.
The spark revealed lightning for what it really was. It was the same as the electricity made by man.
It's hard to overestimate the significance of this moment. Nature had been mastered. Not only that, but the wrath of God itself had been brought under the control of mankind. It was a kind of heresy.
Franklin's experiment was very important because it showed that lightning storms produce or are produced by electricity, and that you can bring this electricity down, that electricity is a force of nature that's waiting out there to be tapped.
Next, Franklin turned his rational mind to another question. Why the Leyden jar made the biggest sparks when it was held in the hand? Why didn't all the electricity just drain away? And drawing on his experience as a successful businessman, he saw something no one else had. That, like money in a bank, electricity can be in credit, what he called positive, or debit, negative.
For him, the problem of the Leyden jar is a problem of accountancy. Franklin's idea was every body has around it an electrical atmosphere. And there's a natural amount of electric fluid around each body. If there's too much, we'll call it positive. If there's too little, we'll call it negative. And nature is organized so the positives and the negatives always want to balance out, like an ideal American economy.
Franklin's insight was that electricity was actually just positive charge flowing to cancel out negative charge, and he believed this simple idea could solve the mystery of the Leyden jar. As the jar is charged up, negative electrical charge is poured down the wire and into the water. If the jar rests on an insulator, a small amount builds up in the water. But if instead the jar is held by someone as it's being charged, positive electric charge is sucked up through their body from the ground to the outside of the jar, trying to cancel out the negative charge inside. But the positive and negative charges are stopped from cancelling out by the glass, which acts as an insulator. So instead, the charge just grows and grows on both sides of the glass. Then, touching the top of the jar with the other hand completes a circuit, allowing the negative charge on the inside to pass through the hand to the positive on the outside, finally cancelling it out. The movement of this charge causes a massive shock and often a spark. The modern equivalent of the Leyden jar is this, the capacitor, and it's one of the most ubiquitous of electronic components. It's found everywhere. There are a number of smaller ones scattered around on this circuit board from a computer. They help smooth out electrical surges, protecting sensitive components, even in the most modern electric circuit. Solving the mystery of the Leyden jar and recognizing lightning as merely a kind of electricity were two great successes for Franklin and the New Enlightenment movement. But the forces of trade and commerce, which helped fuel the Enlightenment, were about to throw up a new and even more perplexing electrical mystery. A completely new kind of electricity.
This is the English Channel. By the 17th and 18th centuries, a good fraction of the world's wealth flowed up this stretch of water from all corners of the British Empire and beyond, on its way to London. Spices from India, sugar from the Caribbean, wheat from America, tea from China. But of course, it wasn't just commerce.
New plant and animal specimens from all over the world came flooding into London, including one
that particularly fascinated the electricians. Called the torpedo fish, it'd been the stuff of fishermen's tales. Its sting, it was said, was capable of knocking a grown man down. But as the electricians started to investigate the sting, they realized it felt strangely similar to a shock from a Leyden jar. Could its sting actually be an electric shock? At first, many people dismissed the torpedo fish's shock as occult. Some said it was probably just the fish biting. Others that it couldn't be a shock because without a spark, it just wasn't electricity. But for most, this was a very strange and inexplicable new mystery. And it would take one of the oddest yet most brilliant characters in British science to begin to unlock the secrets of the torpedo fish. This is the only picture in existence of the pathologically shy but exceptional Henry Cavendish. This one only exists because an artist sketched his coat as it hung on a peg, then filled in the face from memory. His family were fantastically rich. They were the Devonshires, who still own Chatsworth House in Derbyshire. But Henry Cavendish decided to turn his back on his family's wealth and status, to live in London near his beloved Royal Society, where he could quietly pursue his passion for experimental science. When he heard about the electric torpedo fish, he was intrigued. A friend wrote to him, "On this, my first experience of the effect of the torpedo, I exclaimed that this is certainly electricity. But how?" And to work out how a living thing could produce electricity, he decided to make his own artificial fish. These are his plans. 2 Leyden jars shaped like the fish, which were buried under sand. When the sand was touched, they discharged, giving a nasty shock. His model helped convince him that the real torpedo fish was electric, but it still left him with a nagging problem. Although both the real fish and Cavendish's artificial one gave powerful electric shocks, the real fish never sparked. Cavendish was perplexed. How could it be the same kind of electricity if they didn't both do the same kinds of things? Cavendish spent the winter of 1773 in his laboratory trying to come up with an answer. And in the spring, he had a brainwave. Cavendish's ingenious answer was to point out a subtle distinction between the amount of electricity and its intensity. The real fish produced the same kind of electricity, it's just that it was less intense. Now, for a physicist like me, this marks a crucial turning point because it's the moment when 2 genuinely innovative scientific ideas first crop up. What Cavendish refers to as the amount of electricity, we now call electric charge. And his intensity is what we call the potential difference or voltage. So the Leyden jar's shock was high voltage but low charge, whereas the fish was low voltage and high charge. And it's possible to actually measure that. Hiding at the bottom of this tank under the sand is the torpedo marmorata, and it's an electric ray. You can just see its eyes protruding from the sand. This is a fully grown female, and I'm going to try and measure the electricity it gives off with this bait. I've got this fish connected to a metal rod and hooked up to an oscilloscope to see if I can measure the voltage as it catches its prey. So here goes. Oh, there's one.
And there's another one.
The fish gave a shock of about 240 volts, the same as mains electricity, but still roughly 10 times less than the Leyden jar.
Well, that would have given me quite a nasty shock. And I can only try and imagine what it must have been like for scientists in the 18th century to witness this. An animal, a fish, producing its own electricity.
Cavendish had shown that the torpedo fish made electricity, but he didn't know if it was the same kind of electricity as that made from an electrical machine.
Is the electrical shock that a torpedo produces, is it the same as produced by an electrical machine? Or are there two kinds? Is there a kind that's generated artificially, or is there a kind of animal electricity that only exists in living bodies? And this was a huge debate that divided opinion for several decades.
And out of that bitter debate came a new discovery. The discovery that electricity needn't be a brief shock or spark, but could actually be continuous. And the generation of continuous electricity would ultimately propel us into our modern age. But the next step in the story of electricity would come about because of a fierce personal and professional rivalry between two Italian academics.
This is Bologna University, one of the oldest in Europe. In the late 18th century, the city of Bologna was ruled from papal Rome, which meant that the university was powerful but conservative in its thinking.
It was steeped in traditional Christianity, one where God ruled earth from heaven, but that the way he ran the world was hidden from us mere mortals. We were not meant to understand him, only to serve him. And one of the university's brightest stars was the anatomist Luigi Alisio Galvani. But in a neighboring city, a rival electrician was about to take Galvani to task.
This is Pavia, only 150 miles from Bologna, but by the end of the 18th century, worlds apart politically. It was part of the Austrian Empire, which put it at the very heart of the European Enlightenment, liberal in its thinking, politically radical, and obsessed with the new science of electricity. It was also home to Alessandro Volta. Alessandro Volta couldn't have been more unlike Galvani. From an old Lombardy family, he was young, arrogant, charismatic, a real ladies' man, and he courted controversy. Unlike Galvani, he liked to show off his experiments on an international stage to any audience.
Volta's ideas were unfettered by Galvani's religious dogma. Like Benjamin Franklin and the European Enlightenment, he believed in rationality, that scientific truth, like a Greek god, would cast ignorance to the floor. Superstition was the enemy, reason was the future. Both men were fascinated by electricity, and both brought their different ways of seeing the world to bear on it.
Galvani had been attracted to the use of electricity in medical treatments. For instance, in 1759, here in Bologna, electricity was used on the muscles of a paralyzed man. One report said it was a fine sight to see the mastoid rotate the head, the biceps bend the elbow.
In short, to see the force and vitality of all the motions occurring in every paralyzed muscle subjected to the stimulus. Galvani believed these kinds of examples revealed that the body worked using animal electricity, a fluid that flows from the brain through the nerves into the muscles where it's turned into motion. And he devised a series of grisly experiments to prove it. Now, he first prepared a frog. He writes, "The frog is skinned and disemboweled, only their lower limbs are left joined together, containing just the crural nerves." Well, I've left my frog mostly intact, but I've exposed the nerves that connect to the frog's legs. Then he used Hawksby's electrical machine to generate electrostatic charge that would accumulate and travel along this arm and out through this copper wire. Then he connected the charge-carrying wire to the frog and another to the nerve just above the leg. Let's see what happens. Oh, and the frog's leg twitches just as he makes contact. There we go.
Now, for Galvani, what was going on there was that there's a strange, special kind of entity in the animal muscle, which he calls animal electricity. It's not like any other electricity. It's intrinsic to living beings.
But for Volta, animal electricity smacked of superstition and magic. It had no place in rational and enlightened science. Volta saw the experiment completely differently to Galvani. He believed it revealed something totally new. For him, the legs weren't jumping as a result of the release of animal electricity from within them, but because of the artificial electricity from outside. The legs were merely the indicator. They were only twitching because of the electricity from the Hawksby machine. Back in Bologna, Galvani reacted furiously to Volta's ideas. He believed Volta had crossed a fundamental line from electrical experiment into God's realm, and that was tantamount to heresy.
To have a kind of spirit like electricity, to have that produced artificially, and to say that that spirit, that living force, that agency was the same as something produced by God, that God had put into a living human body or a frog's body, that seemed sacrilegious to them because it was eliminating this boundary between God's realm of the divine and the mundane realm of the material.
Spurred on by his religious indignation, Galvani announced a new series of experimental results which would prove that Volta was wrong. During one of his experiments, he hung his frogs on an iron wire and saw something totally unexpected. If he connected a copper wire to the wire the frog was hanging from, and then touched the other end of the copper to the nerve, it seemed to him that he could make the frog's leg twitch without any electricity at all.
Galvani came to the conclusion that it must have been something inside the frogs, even if dead, that continued for a while after death to produce some kind of electricity.
And the metal wires were somehow releasing that electricity. Over the next months, Galvani's experiments focused on isolating this animal electricity using combinations of frog and metal, Leyden jars and electrical machines. For Galvani,
These experiments were proof that the electricity was originating within the frog itself. The frog's muscles were Leyden jars, storing up the electrical fluid and then releasing it in a burst. On the 30th of October 1786, he published his findings in a book, De Animali Electricitati, of animal electricity. Galvani was so confident of his ideas, he even sent a copy of his book to Volta. But Volta just couldn't stomach Galvani's idea of animal electricity. He thought the electricity just had to come from somewhere else. But where?
In the 1790s, here at the University of Pavia, almost certainly in this lecture theatre, which still bears his name, Volta began his search for the new source of electricity. His suspicions focused on the metals that Galvani had used to make his frog's legs twitch. His curiosity had been piqued by an odd phenomenon that he'd come across: how combinations of metals tasted. He found that if he took two different metal coins and placed them on the tip of his tongue, and then placed a silver spoon on top of both, he got a kind of tingling sensation, rather like the tingling you'd get from the discharge of a Leyden jar.
Volta concluded that he could taste electricity and that it must be coming from the contact between the different metals in the coins and spoon.
His theory flew in the face of Galvani's. The frog's leg twitched not because of its own animal electricity, but because it was reacting to the electricity from the metals.
But the electricity his coins generated was incredibly weak. How could he make it stronger? Then an idea came to him as he revisited the scientific papers from the great British scientist Henry Cavendish, and in particular his famous work on the electric torpedo fish.
He went back and took a closer look at the torpedo fish, and in particular the repeating pattern of chambers in its back. He wondered whether it was this repeating pattern that held the key to its powerful electric shock.
Perhaps each chamber was like his coins and spoon, each generating a tiny amount of electricity. And perhaps the fish's powerful shock results from the pattern of chambers repeating over and over again. With growing confidence in his new ideas, Volta decided to fight back by building his own artificial version of the torpedo fish.
So he copied the torpedo fish by repeating its pattern, but using metal. Here's what he did. He took a copper metal plate and then placed above it a piece of card soaked in dilute acid. Then above that, he took another metal and placed it on top. What he had here was exactly the same thing as Galvani's two wires. But now, Volta repeated the process. What he was doing here was building a pile of metal. In fact, his invention became known as the pile. But it's what it could do that was the really incredible revelation. Volta then tried his pile out on himself by getting two wires and attaching them to each end of the pile and bringing the other ends to touch his tongue. He could actually taste the electricity. This time it was more powerful than normal, and it was constant.
He'd created the first battery.
The machine was no longer an electrical and mechanical machine. It was just a purely electrical machine. So he proved that a machine imitating the fish could work, that what he called the metal or contact electricity of different metals could work. And that he regarded as his final winning move in the controversy with Galvani.
What Volta's pile showed was that you could develop all the phenomena of animal electricity without any animals being present. So, from the voltaic point of view, it seemed as if Galvani was wrong. There's nothing special about the electricity in animals. It's electricity, and it can be completely mimicked by this artificial pile.
But the biggest surprise for Volta was that the electricity it generated was continuous. In fact, it poured out like water in a stream. And just as in a stream where the measure of the amount of water flowing is called a current, so the electricity flowing out of the pile became known as an electrical current. "200 years after Volta, we finally understand what electricity actually is. The atoms in metals, like all atoms, have electrically charged electrons surrounding a nucleus. But in metals, the atoms share their outer electrons with each other in a unique way, which means they can move from one atom to the next. If those electrons move in the same direction at the same time, the cumulative effect is a movement of electric charge. This flow of electrons is what we call an electric current." Within weeks of Volta publishing details of his pile, scientists were discovering something incredible about what it could do. Its effect on ordinary water was completely unexpected. The constant stream of electric charge into the water was ripping it up into its constituent parts, the gases oxygen and hydrogen. Electricity was heralding the dawn of a new age where electricity ceased being a mere curiosity and started being genuinely useful. With constant flowing current electricity, new chemical elements could be isolated with ease, and this laid the foundations for chemistry, physics, and modern industry. Volta's pile changed everything. The pile made Volta an international celebrity, feted by the powerful and the rich. In recognition, a fundamental measure of electricity was named in his honor, the volt. But his scientific adversary didn't fare quite so well. Luigi Alizio Galvani died on the 4th of December 1798, depressed and in poverty. For me, though, it's not the invention of the battery that marks the crucial turning point in the story of electricity. It's what happened next. It took place in London's Royal Institution. It was a moment that marked the end of one era and the beginning of another. It was overseen by Humphrey Davy, the first of a new generation of electricians, young, confident, and fascinated by the possibilities of continuous electrical current. So in 1808, he built the world's largest battery. It filled an entire room underneath the Royal Institution. It had over 800 individual voltaic piles attached together. It must have hissed and breathed sulfurous fumes. In a darkened room lit by centuries-old technology, candles and oil lamps, Davy connected his battery to 2 carbon filaments and brought the tips together. The continuous flow of electricity from the battery through the filaments leapt across the gap, giving rise to a constant and blindingly bright spark. Out of the darkness came the light.
Davy's arc light truly symbolises the end of one era and the beginning of our era, the era of electricity.
But there's a truly grisly coda to this story. In 1803, Galvani's nephew, one Giovanni Aldini, came to London with a terrifying new experiment. A convicted murderer called George Forster had just been hanged in Newgate. And when the body was cut down from the gallows, it was brought directly to the lecture theatre where Aldini started his macabre work.
Using a voltaic pile, he began to apply an electric current to the dead man's body.
Then, Aldini put one electrical conductor in the dead man's anus and the other at the top of his spine. Forster's limp, dead body sat bolt upright and his spine arched and twisted. For a moment, it seemed as though the dead body had been brought back to life.
It appeared as though electricity might have the power of resurrection. And this made a profound impact on a young writer called Mary Shelley.
Mary Shelley wrote one of the most powerful and enduring stories ever. Based partly here on Lake Como, Frankenstein tells the story of a scientist, a galvanist, probably based on Aldini, who brings a monster to life using electricity. And then, disgusted by his own arrogance, he abandons his creation. Just like Davy's arc lamp, this book symbolizes changing times, the end of the era of miracles and romance, and the beginning of the era of rationality, industry, and science.
And it's that new age we explore in the next programme. Because at the start of the 19th century, scientists realised that electricity was intimately connected with another of nature's mysterious forces, magnetism. And that realisation would completely transform our world.
To find out more about the story of electricity and to put your power knowledge to the test, try the Open University's interactive energy game. Go to bbc.co.uk/electricity and follow links to the Open University.
And the story of electricity continues here on BBC HD on Thursday at 11. Coming up next this evening, we're paying our regular monthly visit to the sky at night.